In this video I'll go over the 2022 Unit 3 Practical Booklet B. Question 1 Part A then, what is meant by the term solubility? Well, that's just a standard definition. The mass of solid required to saturate 100 grams of water at a particular temperature. Part B then just requires these results to be plotted on the graph, which we'll see on the next page. So here I've plotted the results. And then part 2, have to use the graph to determine the temperature at which the solubility of the potassium chloride is 48 grams per 100 grams of water. So I just find the solubility of 48 and go across and then read down. And I get an answer of 67 degrees C. Don't forget the units. Part 3. So here I have to calculate the mass of solid which crystallises out of the solution when the saturated solution of potassium chloride containing 80 grams of water, okay, so this is important here, is cooled from 70 to 10 degrees C. So this line represents the saturated solution. That's the maximum mass required to saturate the solution. Remember, this is grams per 100 grams of water. So you need to work out the values per 100 grams of water first, and then we'll convert it to 80 grams of water. So what I'm going to do is work out the solubility at 70 degrees C and then at 10 degrees C. So from my graph, I can see that at 70 degrees C, the solubility is 49 grams per 100 grams of water. And at 10 degrees C, again, I just go to 10, go up and read it there, and I see that that is 31. That's all really I need, but I'm going to put in units, like so. Now the difference in solubility is 18. Now remember, that is per 100 grams of water. So always work out calculations based on the graph first, per 100 grams. Now we're going to work out what it is if 80 grams of water were present. Well, if 18 grams would crystallise out in 100 grams of water, then what we do is work out 80 grams of water. So we divide this by 100 multiplied by 80. So it's going to be 18 divided by 100 multiplied by 80. And that works out to be 14.4 grams. Part 4, we've got 10 grams of potassium chloride in 20 grams of water at 50 degrees C. This is a saturated solution. Calculate the mass which did not dissolve. So again, what you've got to do is work out the mass that would dissolve in 100 grams of water at 50 degrees C. From my graph, I can see that's 43. Again, that's grams per 100 grams of water. I'm going to put it in this time. So what I can do now is work out what the solubility would be, again, still at 50 degrees C, in 20 grams of water. Well, to go from 100 to 20, that's obviously dividing by 5. So what I can do is divide this 43 by 5. And that is 8.6. Now in the question, 10 grams were originally placed in the 20 grams of water. And the question is, calculate the mass of potassium chloride which did not dissolve. So if you added 10 grams to start with, 8.6 grams dissolved, that means that the difference is the mass of potassium chloride which did not dissolve, and that is 1.4 grams. Here we've got the reaction of calcium with water. Write a balanced symbol equation for the reaction. Well, a metal plus water will give the metal hydroxide. Remember, calcium has a valency of 2, hydroxide has a valency of 1. To swap those, the brackets must go around the OH, but these are different elements. And then hydrogen is produced. That needs to be balanced when a 2 goes in front of the water. 2 other observations which could be made, or which would be made, when calcium reacts with water. So be careful here. You're told that heat is released the calcium sinks and then rises in the water. So two other observations. Well, when a metal reacts with water, there will be fizzing or bubbles given off. The metal disappears or the calcium disappears, and that's two things for 2 marks. You could also say that a white solid's formed or a cloudy solution's formed, because remember, when group 1 reacts with water, you get a colourless solution. But when calcium reacts with water, the solution's cloudy, and that's because a white precipitate or a white solid forms in it. Part B then has to do with the apparatus below. So I've put the diagram at the bottom of the page. And then part 1, what labels should be placed at A and B? Well, A is mineral wool or damp mineral wool. So it does have to be damp because when it's heated that generates the steam. And then B is a delivery tube. Part 2, balance assembly equation for the reaction of aluminium with steam. Now it's important to remember that when a metal reacts with water, the metal hydroxide is formed along with hydrogen. But when a metal reacts with steam, the metal oxide is formed. So this is going to be aluminium oxide, not aluminium hydroxide. Hydrogen is still formed. And that needs to be balanced. And it does say that state symbols have to be included. Well, aluminium is a solid, it's a metal. The H2O is a gas because this is steam. Again, be careful with that. Aluminium oxide is an ionic compound. That's going to be a solid, high melting point. And then hydrogen is a gas. And part 3, suggest why the bung is removed from the boiling tube as soon as heating is stopped. Okay. If you just pull the heating away and you leave the apparatus as it is, a vacuum is created in here and that will suck water back up into the boiling tube, and that can break the boiling tube because the glass is hot. So we just call that suck back. So what we would do is remove the bung. Now the question is saying remove it as soon as heating is stopped. What we would often do is actually remove the bung first before we take the heating away, although that can be difficult because the apparatus can be very hot. But anyway, regardless of that, the reason why the bung is removed as soon as heating is stopped is to prevent suckback. Part C, I'm just going to go to part 1 here. Iron 2 nitrate is green, the solution is green. Predict what you would observe when magnesium reacts with iron 2 nitrate. Well, in this reaction, the magnesium will react with the iron 2 nitrate to form magnesium nitrate solution. And magnesium nitrate solution is colourless. So the solution will go from green to colourless. Now that will obviously depend on how long the magnesium is left. So you might just see there that the green solution fades. It actually just gets a lighter colour. Heat is also going to be produced. And the other product of the reaction is iron. Now, iron is a grey solid, so you could say a grey solid or even a black solid forms. And then part 2, arrange these from most reactive to least reactive. Well, we're looking at the number of ticks. You can see that magnesium reacts with all of them. There are 3 ticks. The iron has 2 ticks. Cobalt has 1. The copper has none, so it's the least reactive. Question 3, identifying some ions. This will take us back to year 11 work or 4th form work. So use the evidence from test 1 to identify a cation present. Well, you can see in test 1 here, there's a lilac flame. So that tells us that the ion is potassium. So I'm going to put in the word, or what you can do is the symbol. Now, if you're putting in the symbol, you need to do it K+, not just K, because that's a potassium atom. Okay, and it has asked us specifically for the cation. So either say the word potassium or K+. On to the next part. So test 2, identify 2 other cations which may be present. So let's read what it says here. The mixture is dissolved If it's a solid to start with, you dissolve it in water. 5 drops of sodium hydroxide were added. And you can see here that a white precipitate is formed. So that means that the ions present could be magnesium or zinc or aluminium. So then we have to read on. An excess of sodium hydroxide solution was added. The precipitate disappeared. Okay, so that eliminates magnesium because the precipitate formed from magnesium ion solution remains. Therefore, this indicates or tells us that aluminium and zinc ions could be present. Part 3, using the evidence from test 3, write the formula of the anion present. Well, in test 3, 5 drops of silver nitrate solution are being added. Now, when you hear silver nitrate solution being used, you should automatically be thinking, okay, this is testing for halide ions. Chloride, bromide, iodide. The fact that a white precipitate is formed tells us that the ion is chloride. So we have to write the formula, not the name this time. So Cl minus. An ionic equation then for the formation of the white precipitate. Silver nitrate solution was being used, and it says silver ions from silver nitrate solution, which take part in this reaction. They react with the chloride ions to form silver chloride. That's the white precipitate. Now, we have to put in state symbols as well. Well, the silver nitrate is a solution, so it's aqueous. The chloride ions were in solution, they're aqueous. And then the white precipitate is a solid, so it's S. Suggest the name of a compound which may be present. Well, we had identified from the lilac flame that there's potassium ions present, and then the sodium hydroxide solution indicates it could be zinc or aluminium ions present. And then we know from the silver nitrate reaction that there's a chloride. So what you could put is potassium chloride or zinc chloride or aluminium chloride. In part B, I describe how you would carry out a flame test. 4 marks, so a bit of detail is required. We're going to start off with a nichrome wire. It's going to be dipped in concentrated hydrochloric acid and is then placed into the sample, and then that's put into a blue Bunsen flame. Question 4, part A, is just recalling the definition of water crystallization. B then, describe the method used to determine the value of X, so in other words, to calculate water crystallization. Well, for the apparatus used, you can use a crucible or you can use an evaporating basin. So let's see. I'm going to put in evaporating basin. And for it, we need a tripod and wire gauze. Now, if you used a crucible, wire gauze wouldn't be used, but a pipe clay triangle would be needed. So be careful of that. You still need a tripod, and then we're going to need a Bunsen burner as well with those. Then the sample is going to be weighed. So you weigh the evaporating basin or the crucible with the hydrated salt. You would then heat this, re-weigh it, and you would do that until the mass stays the same. In other words, you heat to constant mass. This final mass can then be subtracted from the initial mass, and that will determine the mass of water crystallization. Part C. Describe a chemical test to confirm the liquid is water. Now, we're not going to test the boiling point here because it's asking for a chemical test. So the test we use is anhydrous copper 2 sulfate, which is white. And if water is present, it will change to blue. Part D, calculate the loss in mass when a sample of 1.23 grams of the hydrated magnesium sulfate was heated. So I'm just going to write the equation here to show the decomposition of this hydrated salt. So when that's heated, it'll go to anhydrous magnesium sulfate, MgSO4, and 7 waters will be lost. So what we can do is work out the number of moles of the hydrated salt. Now the RFM of all of this is 246. If you're not sure how to do that, work out this bit. So the magnesium's 24, 32 and 4/16. And then you add on 7/18. That all comes to 246. So that equals 0.005 moles. So then if you look at the ratio, you can see that it is a 1:7 ratio. So I'm multiplying this by 7, and that works out to be 0.035 moles. This can now be converted to a mass of the water, which is 0.035 times the MR, or the RFM of water, which is 18, and that's 0.63 grams. So that just goes in here, 0.63. Question 5 is about a titration. Well, the first part of the question is asking you to describe how you would prepare and then use a pipette. Now, when you're using a pipette, or indeed a burette, you always rinse it out with whatever you're putting into it and with deionized water. So I'm just going to start off here by saying rinse with deionized water, and then rinse with the unknown metal hydroxide solution. Now just make sure you put in the word solution here. And again, that'll ensure you get the mark for that. You're using a pipette. It has to be used safely. So we're going to use a pipette filler. The metal hydroxide will then be drawn up until the bottom of the meniscus is on the line. You would then transfer this to a conical flask, release it into the conical flask, and then touch the tip of the pipette on the surface of the liquid. Part B then, state the colour change. Okay, so I'm going to have to read through what exactly is happening here. So titration is carried out. We're trying to find MOH2. The metal hydroxide was dissolved, and then 25 was transferred to conical flask. So if I just sketch that over here, this is the metal hydroxide solution. That's the alkali. And then it was titrated against hydrochloric acid. So the hydrochloric acid is going to be in the burette. Now in alkaline solution, methyl orange, which is the indicator being used, is yellow. And then it will go to red. See, 2 ways you would ensure that the endpoint is determined accurately. So any two from dropwise near the endpoint, read from the bottom of the meniscus. A third one you could have there is swirl the conical flask. So just remember those three. So those three are always the answers for ensuring titrations are determined accurately, or the endpoint is determined accurately. Okay, the average titer here. Well, remember, don't use the rough titration. The rough titration is carried out just to speed up the overall titration. So we're going to use the accurates, and it's going to be an average of these two values. So that is 12.5 cubic centimetres, include units. On to part 2, calculate the number of moles of hydrochloric acid used. Now this is the information from the start of the question. To work out the number of moles, I'm going to multiply concentration by the volume. The volume of hydrochloric acid is 12.5. That has just been calculated. So it's going to be 12.5 times the concentration of hydrochloric acid, which is 0.16, and It's got to be divided by 1,000 to turn the 12.5 cubic centimetres into decimeters cubed. So that works out to be 0.002 moles. Of course, what you could do is change that. Part 3, calculate the number of moles of the MOH2, the hydroxide solution present. I've just worked out the number of moles of HCl, and you can see it's a 2-to-1 ratio. So the number of moles of HCl were 0.002. Therefore, this is going to be 0.001. Part 4, calculate the number of moles in 1 cubic decimeter. So this number of moles are present in 25 cubic centimetres. Now, a cubic decimeter is 1,000 centimetres cubed. Well, to go from 25 to 1,000, we multiply by 40. So you can just simply multiply this answer by 40. It's going to be 0.001 times 40, and that equals 0.04 moles per cubic decimeter. Part 5, using the initial mass, and now the initial mass was 6.84 grams. And the answer to part 4, that was just calculated and worked out to be 0.04. So now we have to calculate the relative formula mass of this MOH. We've got a mass, we've got moles per decimeter cubed, so mass over the RFM or the MR. We're after the MR. Rearrange this equation. So the MR is going to be the mass, which is 6.84, divided by the moles, 0.04. 171. So calculate the relative atomic mass of M. Well, we know what OH2 is. We can work that out using the periodic table. So I'll just do that. So OH2, well, that's 16, that's 17 times 2, 34. So that means the M equals 171, which is worked out here. Remember, that is the RFM of the whole thing. So 171 minus 34 works out to be 137, and this is the mass. Then use your periodic table, find out which element has a relative atomic mass of 137, and it's barium. Identity, that means you can do the symbol or the name.